but we already have a microscope lab on Tuesday. And then we're going to not do hemostasis today, but we're going to do blood typing, because our lab today is blood typing. Okay? So this image here is showing taking of blood. This is from veins. And they have this kind of, the blood doesn't usually taken from that vein. Most of you know it's taken from one of the veins in the cubital area. It might be the median cubital, or it might be one of the median facilic. It depends on which one is closest to the surface. And is usually taken up into a vacuum tube. So a needle is inserted, and then a vacuum tube with no air in it, low pressure, is put on that. I was having blood drawn when I was teaching back east. They were telling us our health insurance rates would stay low if everybody had physicals and went on this promise to run every day and that kind of thing. So they turned the gym into a big clinic where they were doing blood pressures and weights and blood draws and stuff. And one of my former nursing instructors was drawing blood for me, and I teasingly told her that if she didn't do it right the first time, I was never going to be her friend again. Well, she proceeded to need to try 5 times. And she said, I don't know what's going on. She said, I can actually feel the needle, the give, when the needle goes through the vessel wall. But when I put the tube on there, nothing happens. And what we finally figured out after the 5th time was all the tube, she was using the same tube, and the vacuum, the O-ring was gone. And so there was no vacuum in it, so there was no draw on the blood, so suction for that, so she had to replace it. But anyway, typically we draw these up into tubes, and then they're stored. To run a hematocrit, which is what's being shown on that particular diagram, when we used to do body fluid labs, which we no longer do anymore, they would be drawn up with a capillary tube. And I just saw some everything. Here we go. They would be drawn up in a capillary tube, which are small, fine glass tubes that are hollow and open on both ends. You've probably heard of capillary action. So when we add solution sometimes to a microscope slide, you just put it on the edge of the slide, and capillary action draws it up under the slide. So if you were to poke your finger with a lancet, this is a really tiny opening, and just put it on the edge of the tube, that would draw it up into the tube. And then we would place it in one of these strips of clay. Just push it down in there like that. And when you pull it up, there's a plug at the bottom filled with the clay. The reason you want a plug is when you put it in the centrifuge, and this would have a flat. Let me show you an image of one towards the end of the red blood cells here. This centrifuge has tubes. Has grooves in it, and you would lay the glass tube into that. And if you had that end open, as it started to spin, you'd have blood everywhere inside your centrifuge. All right? Yeah, so we don't do body fluids here. But I wanted you to see what the instrument would look like. We actually have one of these in one of the other lab rooms. It has a little cap that screws down. And so this pulls is gravitational centrifugal force. So when my kids were little, we had 2 sharp turns, right angle turns in the streets just before our house. And so I would be driving along normal street speed, and I would get to the street and just make a real sharp turn to the right first, and they get thrown to the outside of the corner, and they giggle and squeal and everything. So that's a centrifugal force. So we do this over and over for 3 minutes. The heavy material is pulled to the bottom or pushed to the bottom, and that's what we call the formed blood cells. The red blood cells, the white blood cells, and the platelets. And so that's, you can see here that the plasma is pretty clear, and when you look at the edge of it, you can see a light area that's formed of the white blood cells. But most of the cells in the blood are red blood cells. Let's go back to this previous component here. And so on the first page of the lab activity for blood, I've drawn out some sample capillary tubes. So there's about 5 of them, I think. And normally it doesn't matter how much blood you put in. It just, so if you have a tube, you may fill one tube to here. You may fill another tube to there. So when you spin it down, and you have your measurement of the red blood cells, you're measuring the length of this amount where all the cells are, and dividing by the total length of the blood. So it doesn't matter what that total length is if you do it separately for each tube.
And what does that give you?
It gives you a percent of red blood cell primarily, but it's usually all cells, over total volume. So this is identified as hematocrit. Okay? And we're doing it not by volume, but using the length to represent the volume. So you take A and divide by D, and you'll get some number that looks like 39, whatever. That's not, so then you have to multiply by 100, move your decimal point over 2, and so that's going to equal 39.2%. So hematocrit is always expressed in percentile. Okay? And we'll come back to this at the end when we talk about various blood tests that we use to determine how much red blood cell or hemoglobin is present. But for right now, I want to look at it as a reference to what we find in the blood. So blood, approximately 45% of blood is the red blood cells. Another 3 to 4% would be the white blood cells and the platelets. And about 55% or so will be the plasma. So the plasma is the fluid, but it's not a clear fluid. All right, it's not a pure water. It has proteins that are dissolved in it. So we have albumin and globulin and various regulatory proteins and clotting proteins. Most of these proteins are synthesized by the liver. And before we look at what they do, if we take the clotting proteins out, the plasma is then identified as serum. So rephrase it, sera is plasma minus proteins, the clotting proteins, that is. So today in lab, we're using some fake blood and some fake serum, which has antibodies to the A or the B or the D antigen. So that would be, say we took some blood from a mouse that had been exposed to A antigen, and it made antibodies against it. And we took out all the cells and kept the serum, but it would clot too, so we took out the clotting proteins. That would be just the serum. Or if you have a snake bite and you are given an anti-venom serum, that would have been taken. Usually those are made in horses because they have a large blood volume, and it's economically more feasible. They don't need to kill the horse, they just draw the blood. So they'll inject a minute amount of the toxin, not enough to kill the horse, but to cause it to develop an immune response. And then they'll draw blood from that horse, spin it down, take out the cells, remove the clotting proteins, and then just sell the rest as the anti-snake toxin given serum. So albumin is the most common protein. Notice it's spelled with an I, not an E. It's not the same albumin that we see in egg whites. It's made by the liver. Its primary function is to help maintain osmotic pressure. This was something, there was a question
on our study guide.
Sample exams and the study guide. And I said, never mind, we'll get to it in this unit. So I'm going to introduce you to it today, but we'll look at it again on tomorrow. So if we look at the layout of our vascular system, and we have arteries, and then we have our capillary bed.
Oh, I have it right.
And then we have our veins. Which end, the arterial end or the venous end, is going to have a higher blood pressure? closer to the arteries. And what was another phrase for blood pressure? Hydrostatic pressure. So the pressure created by the volume of blood in the heart pushing it is hydrostatic pressure, and that's higher it's higher than osmotic pressure, but it's higher on this end and lower on the venous end. Okay? Because of that higher hydrostatic pressure, on this end, we tend to lose water across the capillary bed wall. So remember we talked about having congestive heart failure? And the blood backs up in the left atrium and into the pulmonary system. Fluid is pushed into the alveolar sacs, causing pulmonary edema. And if we have right-sided congestive heart failure, blood is pushed back into the right atrium, into the vena cava, and into the capillary beds. You get swollen ankles and fingers and systemic edema. So it's a similar factor, just not as much fluid is lost. So this is going on all the time. Helping to prevent as much fluid loss as might occur, we have proteins such as albumin present in the blood. And I don't know, those of you that didn't have me last semester, did you do a dialysis experiment where you had glucose or starch in dialysis bags and they couldn't leave the bag but they pulled water toward themselves? All right, so it's a similar situation here. Proteins are too large to leave the blood vessels. And so they have an osmotic pull.
Okay, no, we did with onion. Yeah, we did with onion and alcohol.
Same
Yes,
thing.
we did, yeah.
So they have an osmotic pull on the water, either attracting water into the capillary or keeping water that's in the artery from leaving. So these proteins then create, or albumin, create an osmotic pressure, sometimes called a colloidal pressure, which is in the opposite direction. It's lower on the arterial side. For two reasons, hydrostatic pressure is dropped because we're farther away from the heart, and hydrostatic pressure also drops because we've lost some of the volume. So hydrostatic pressure is dropped, therefore we have a higher concentration of the proteins. We don't gain more proteins, we just have lost some of the fluid. And so hydrostatic pressure on this side becomes greater, and we actually pull back osmotic pressure becomes greater. We actually pull back water into the cardiovascular system. Not all of it. So we do end up with a net loss of fluid to the connective tissue, and that's where we'll come back tomorrow, because that's how we use the lymphatic system, is to return that net loss of fluid back to the cardiovascular system. Okay, I'm just illustrating here what albumin does. If somebody has liver failure, either from hepatitis or cancer, they tend to get an enlarged abdomen because they have insufficient albumin. Hydrostatic pressure is always greater than osmotic pressure, and they lose fluid into their abdominal cavity. It's known as ascites. And doctors will go in there with a cannula and draw off 1 to 2 liters of fluid from the abdominal cavity. It's also the condition in countries where there is very little protein and the diet is poor, and you see stick-thin arms and legs on the children and large swollen tummies. It's not because their tummies are fat, it's because they have the same fluid for the same reason. The liver doesn't have enough amino acids to make sufficient albumin. So the hydrostatic pressure in the capillaries of the abdominal wall lining are losing fluid. All right, globulins are additional proteins. They're typically involved in the transport of material. So, for instance, LDL and HDL are types of globulins. Transferrin carries iron. That's a type of globulin. And then we have other globulins that are immunoglobulins that we'll talk about next week, which are antibodies. Most of our clotting proteins are made by the liver, and we find those inactive in the blood. So tomorrow we'll talk about that activation, what turns it on and when turns it off, and then we have hormones and other chemicals that are being transported by the blood. So the plasma contains these components, not just only water. So now let's look at the blood cells, and we're going to look at red blood cells first. All blood cells, however, develop in the bone marrow. So this slide is unusual in that it shows a whole bunch of white blood cells. Usually you would see only one blood cell, white blood cell, with that number of red blood cells. You might have to move the slide a while to find the others. But all blood cells are formed in the bone marrow. Here's an example of one site of bone marrow location. Flat bones of the hip and the skull and the sternum. Anybody remember what this area or type of bone marrow tissue that we find in the skull is called? It is red, but it's called a specific name starting with D and O with two little dots over the O at the very end. Diploid, yes. All right, so when we look at the location, it changes between the fetus and the adult. So our word for general blood cell formation is hematopoiesis. Erythropoiesis would be just red blood cells, and leukopoiesis would be just white blood cells. Hemato is for both. In the fetus, this takes place in the liver and in the spleen. In the adult, the liver and the spleen are the site where we break down red blood cells. So there is no new red blood cell formation in the liver and the spleen. It also takes place in red bone marrow. And this is trabecular or spongy bone. And in the fetus, we find it in flat bones.
Are we doing fetus already?
Yeah.
Does that say fetus up there already?
Yeah. In the fetus, we find it in flat bones and in long bones, all of the long bones. So the epiphyses and the diaphysis. So I don't know if you remember looking at the cut long bone in Bio430, but the medullary cavity is hollow. And as you run your finger along it, though, it's kind of rough. But in the fetus, that's full of spongy bone. In us, it's yellow marrow or fat. And so they continue to make bone marrow, blood there. In the adult, or post-fetal life, it is in flat bones. And in the epiphyses only of long bone. So the skull is one of our flat bones. The ilia, the ala, the wing of the ala is the most common through the iliac crest for sampling bone marrow or doing bone marrow transfusions. A quick and, well, it's not that big, dirty, but the sampling is the smaller size is the sternum. So when I was working with the medical students at Davis and Gross Anatomy, we would, towards the end of the quarter, we would have medical residents come back to the cadaver lab and practice the sternal task for obtaining bone marrow from the sternum. They do that in the ER. They need a real quick sample. Yeah. Without all the anesthesia, local, all that kind of stuff they do with the other staff. So here's an image of what the range of cell development looks like with hematopoiesis. This is actually erythropoiesis. And you can see two characteristic changes that occur in erythropoiesis. Why would we have a large nucleus at the beginning? What's going on? Why would the nucleus be enlarged? Okay, well, cell division can occur with the nucleus, and obviously we have to replicate the DNA for cell division. What do we also do with uncoiled DNA? DNA is uncoiled for DNA replication, for mitosis, and DNA transcription, for protein synthesis, making a messenger RNA. So in the early stages here, the reason the cell is so purple is the cell is undergoing transcription, making thousands of copies of messenger RNA for the synthesis of what hormone? Not hormone, I'm sorry, what protein? Hemoglobin. There are other enzymes, so the cell is not full of only hemoglobin, but there are other enzymes, cytochrome oxidase and stuff that are involved, but primarily hemoglobin. So once those copies of messenger RNA are formed, the cell no longer needs DNA transcription. The cell is not going to undergo cell division outside of the bloodstream because it doesn't have a DNA. That DNA is, the nucleus is lost to give more room for hemoglobin. So just prior to leaving the bone marrow, the nucleus is extruded, and we end up basically, it's not a live cell, it can't undergo cell division as per se. We're basically left with a membrane sac full of hemoglobin and enzymes, other proteins. At times, the body is under stress to produce additional red blood cells. Either it needs additional oxygen for a short period of time, or it may be some other pathology where it's increased in red cell production, and they're pushed out of the marrow too rapidly before they've lost all of their ER and ribosomal material, and it shows up as these blue strands, and those are called reticulocytes. So the appearance of these in the blood, when you're looking at a